Greetings and welcome to the introduction to astronomy. In this lecture, we are going to talk about the structure of the atom and how spectral lines are formed. Now, we did look at spectral lines last time, and now we're going to see actually how those are formed. So first we want to look at how the atom is set up, and an atom is set up with a nucleus and electrons orbiting around it. Now this is a simplified version that we call the Bohr model of the atom. And that has the nucleus with protons and neutrons, protons being positively charged, neutrons having no charge, and those are concentrated in the nucleus. Now the other ones are the electrons that actually orbit around the atom. And here we see the structure of lithium, but we will look at other atoms. We can look at other atoms as well. Now this is not to scale. This would be vastly different. The nucleus is incredibly tiny compared to the orbits of electrons. Now let's look at a few definitions here that we need to learn. We want to look at isotopes and ions. Isotopes are the same atom. That means they have the same number of protons. It is the number of protons in a nucleus that defines the atom. When you have a different number of neutrons, then the mass has changed. So here we see various isotopes of helium. There's helium 3, helium 4, helium 5, helium 6. Note that every single one of them has two protons. So we see two positive charges here and here. But differs is the mass by the number of neutrons. This one has a mass of 3 because it only has one neutron. This one is 4 with 2 neutrons, 5 with 3, and 6 with 4. So the atom is defined by the number of protons. The isotope then is a different number of neutrons. Now ions are a little different. Ions involve the electrons. So in an ion, electrons have been added or removed from the atom. In this case, the mass stays the same because the mass is all concentrated at the center in the protons and neutrons. However, we can either take away or add an electron. Let's look at taking one away, and there it's gone. And now we still have a helium atom with the same mass. But it is now an ion because it has a charge. It now has a positive charge because we have two positive charges in the nucleus. So two positives and one negative. So it has a net charge of +1. So the difference with the ions is that they have an electrical charge, whereas the ordinary atom is neutral. Now let's look at the Bohr model. And here is the Bohr model for hydrogen. And in the Bohr model, electrons have distinct energy levels, and they can only move between the energy levels. They cannot be between them. So an electron can move in any of the arrows that we see here, but we could not have an electron existing in between the levels any place. That will not happen. And that means that we will never only be able to see them in very certain distinct orbits. So while it may look like a miniature solar system, the planets could be in any orbits. These cannot. Now when we can look, they can change if we move them to a higher energy level that takes energy. So if we take an electron from this level up to this level, that requires energy. It gives off energy if we go from a higher to a lower level. So if we go from a higher to a lower level, that then gives off energy. So moving to a higher level takes energy, moving to a lower level gives off energy. And each of those amounts of energy corresponds to a wavelength then. So what this does is means we get very specific energy levels for each of these. So here we have the different series that we can get depending on which energy level you're transferring to. So if you're transferring to the ground state, n equals 1, you get the Lyman series. Those are very high energy and in the ultraviolet. N equals 2, if you're ending up at that state, you get the Balmer series, which is in the visible. N equals 3, you will get the Paschen series, which is in the infrared, and so on. So what this does is specific wavelengths, only specific wavelengths can be emitted or absorbed. Remember, we saw very specific lines in those emission and absorption spectra. And this gives us a fingerprint for each element has very distinct energy levels. And that allows us to tell the difference between these. So when we look at these here, here is an example of looking at various different atoms, and we see sodium has specific lines, hydrogen, calcium, and mercury. Now some of them may look very close to each other, but the overall pattern is completely different. So if we look for this pattern of lines in an object, then we would know that sodium is present. This pattern would tell us hydrogen, this calcium, and this one would be mercury. So we can look for those distinct patterns that we see. Now in reality, this can get very complex because if we look at something like the sun, and here is an example of a solar spectrum, what we see is it gets really complicated because there are lots of elements there and all have their spectral lines. So if you don't have just one element, it's not quite as easy. You also have that each ionization will give you a different spectrum. So that calcium, neutral calcium, will give you one spectrum. Calcium with one electron removed will give you calcium with two electrons removed will give you a completely different spectrum. And when you start looking at things like molecules, you will get even more complicated spectra. Molecules will absorb bands of light. So complete bands taken out. And these are very prominent in low temperature stars. And again, it gets much more complicated than the simplified version that I've talked about earlier. But overall, you can still analyze and look for those very specific wavelengths to be able to determine what is present in the star. Then we have to know things about temperatures to actually see what their composition is, because just because a line is very strong doesn't mean there's a lot of that element. It may mean that the conditions are just right to excite that element, so it's very strong. There are other elements may be more prominent, but are just not visible. So let's go ahead and finish up here with our summary. And what we looked at is atoms are composed of the protons and neutrons, which make up the nucleus, and the electrons, which orbit around. The electrons can only be in very specific energy levels around the atom. So they can't be in just any place. They have to be in one of those specific energy levels, and they can transfer between them, either giving off or absorbing energy. And this gives each atom its own distinct fingerprint and allows us to determine the composition of various objects in astronomy. So that concludes this lecture on atomic structure and formation of spectral lines. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.